So now that we have the Schwarz inequality, let's proceed. And so what we want is we really want to evaluate the product of sigma a squared and sigma b squared. Let's introduce some notation. So sigma a squared is equal to, for a given quantum state psi, is equal to a minus a, that's squared, psi, and note that a is a physical observable, so it's Hermitian. So I can also write this as a minus a psi inner product with a minus a psi. And so now I'm introducing notation to just make the following calculation a bit more compact. I will actually introduce psi underscore a, where psi underscore a is defined here as a minus a, the quantum state I get when I act with a minus expectation value of a on psi. And similarly, I can write for sigma b squared, I can write that that is equal to psi b with psi b equal to b minus expectation value of b acting on psi. Okay. Schwarz inequality gives me that psi a, if I take sigma a squared times sigma b squared, now expressed in these, in the notation we just introduced. From Schwarz inequality, it immediately follows that this is equal or larger to psi a, psi b squared. Okay, now we are down to further evaluating this side of the inequality. For that, we use that for any complex number z, we can observe that its absolute value squared is equal to the real part of z squared plus the imaginary part of z, and that's squared. Both of these are positive numbers, and so I can say safely that this is larger or equal to imaginary part of z, so I can kind of take out the real part, and then in turn the imaginary part I can actually write as for any complex number, the imaginary part I can always write as 1 over 2i z minus z star. So if I do that, then I can write the imaginary part of z squared as 1 over 2i z minus d star. And note that equality here means that psi a, or I would obtain equality right here if psi a and psi b, psi a and psi b are linearly related by a scalar, and equality here I would get if the real part of z is actually 0. So if z was a purely imaginary number, I would get an equal sign right here. And we'll get back to that in a moment. But okay, so we'll have the Schwarz inequality and that general way, or that general inequality for a complex number z. If I combine these two, I get that psi A, psi B, that is larger or equal than 1 over 2i of, my complex number z is here, the inner product of psi A and psi B. So this is z, z star. I can actually write as through just switching the inner product around, so I can write z star as this, this, and another bracket, n squared. Okay, cool. And so now the last step that we need to do is evaluate psi A and psi B, as well as psi B, psi A, or those two inner products. The inner product of psi A and psi B, I'll write out here, is equal to A minus A psi B minus, B psi. Now A and B are both Hermitian, so I can write this also in this way. Psi. Now I'm going to multiply everything out, so then I have psi, and then I have A times B minus A times expectation value of B minus expectation value of A times B minus minus times minus, so it's plus expectation value of A times expectation value of B, and then finally another psi here. Now, if I use the psi here and here and calculate what that is applied to here, this is just going to give me again A expectation value, B expectation value. So if I evaluate the whole thing, this actually comes out to be simply the expectation value of A times B with respect to psi minus 1 time the expectation value of A minus B. If we do a very similar thing for a very similar calculation for the inner product of psi B and psi A, this will actually turn out to be B times A, the expectation value of B times A, again minus the expectation value of A times B. And if we use this and plug it in right here, we get directly the generalized uncertainty principle. All combined give psi A, psi B is larger than or equal to AB commutator divided by 2i squared. And remember that this was sigma A squared and this was sigma B squared. So we are done. Okay, last comment I wanted to make is, let's get back to, if we wanted to have equality, right, we had two conditions to get actually an equal sign in this inequality, and one was that psi A and psi B had to be linearly related, and then the complex number z here had to be real to get in an equal sign right here. Okay, so what does that mean? So to get equality here, we need that psi A, say, or doesn't matter which way, but let's say psi B, that is equal to alpha times psi A for some alpha. That can be a complex number. But then second, we need that our number z, which is actually the inner product of psi A, psi B, must be imaginary, purely imaginary. Given 1, psi A, psi B here is actually equal to alpha psi A, psi A. The inner product of, quantum state or a vector with itself is always real. So that means alpha must be purely imaginary. So let's write alpha as I times A, where A is real. That would do it. So so the condition then to get a condition for minimum uncertainty for a quantum state psi, and with respect to any observable A and B, then is that psi B, which is B minus B, acting on psi, has to be equal to I times A minus A, acting on psi, with a real. And Griffiths does this for the positional momentum operators. So see Griffiths 3.52 for the case where B is actually the momentum operator and A is the position operator. And you'll see that the result is that psi is a Gaussian. So you can convince yourself that the Gaussian is the minimum uncertainty, or is the shape for a wave function or a quantum state that will give you minimum uncertainty when you're thinking of measuring position and momentum. And the Gaussian is, of course, something that we have explored when we discussed one-dimensional potentials. Okay, so that's it.